Okay, now relevant to problems 8 and 9, which were the questions that motivated this review. We make the premise, in questions 8 and 9, we have, in 1 we have an LC circuit, an inductor, and a capacitor, and in 9 we have an LRC circuit, inductor, capacitor, and resistor. So in both cases, we bypass the whole problem of the differential equations, which we still need to be able to solve, and we simply hypothesize, okay, the current is going to be some cosine function, and this is going to be the case if you have an alternating current circuit, LRC circuit. So AC implies that I of t is I max cosine of omega t, and from this, as we saw, we have VL equals negative omega t, I max sine omega t, the voltage across the inductor, voltage across the capacitor, 1 over omega c times I max sine of omega t. These are both sine functions. We could add them, and we will, to get the total voltage drop across the inductor and capacitor. Okay, well, the phasor that we get from this, and this comes directly out of the review we did a minute ago, or in the last, what do we call these things, video clip. We then conclude that the maximum value of the voltage across the inductor is omega L times I max, the maximum current, and that the voltage across the capacitor is I max over omega c, the angular frequency times the capacitance. And that our phasor diagram therefore looks like this. This vector having magnitude I max over omega c, this vector having magnitude omega L times I max, and the relative sizes of these vectors depend on the relative values of omega L and omega c. Okay, well, our resultant, and I used an arrow over the top here, and I shouldn't have, so let me correct that. Okay, so our resultant voltage is just going to be the sum of these two, and that's going to clearly be this. Okay, now some of our voltages around the circuit, okay, and we're talking about an RLC circuit, and it might be useful if I was to sketch one up here. We'll put a resistor here, an inductor here, and a capacitor here, and a current. Okay. The sum of the voltages around here is 0. Now, the voltages we have for the inductor and the capacitor are the voltage drops across the inductor and capacitor and resistor if we have one. We don't in this particular example, but we will in the next problem. And a voltage of the source. Okay? Well, the source voltage is going to be positive when the voltage drops across these circuit elements are positive. So we can say that the voltage of the source is equal to, in this case, the voltage drop, total voltage drop across both circuit elements, the capacitor and the inductor. Just adding these two expressions. And that's equal to the voltage source. Now, we say, this, don't worry about this 90 degrees just yet. Let's go to the main point here, and then we'll talk about phase angles. So the maximum voltage is going to be what? Well, it's going to be the magnitude of 1 over omega c minus omega L. The way I've drawn these here, your omega c is bigger than your omega L, so you're going to have, this will be positive, and that's the reason I wrote this in the order I did. But, well, it can be written in any order. Okay, so it's very possible that omega L would be bigger than 1 over omega c. and that this would be a negative quantity, which would change the phase of everything. That is irrelevant to finding the maximum voltage, which depends only on the magnitude of omega C and omega L. If this quantity is positive, then you get the maximum voltage when the sign is positive 1. If this happens to be negative, well, the maximum voltage occurs when the sign is negative 1. Okay. So the maximum voltage is just the magnitude of this quantity times I max. And this quantity inside the absolute value signs would be the same if we wrote it omega L minus 1 over omega C. We can then say that the magnitude of 1 over omega C minus omega L, or omega L minus 1 over omega C, magnitude doesn't matter, is the maximum voltage divided by the maximum current. Well, what do you get when you divide a voltage by a current? That gives you the resistance. Okay? This isn't a resistance, but it acts like a resistance in reducing the amount of current you get for a given voltage source. Okay? So, it's like a resistance, but we call it reactance. We've used that term before. This would be magnitude of XC minus XL. And of course, again, you can reverse, since we got magnitude, you could reverse the order of the subtraction.